Robin, thanks for that introduction, and it's a pleasure to be here to tell you about our project entitled Optimized Resins and Sizings for Vinyl Ester Carbon Fiber Composites. I'm going to stand down here. I like to walk, and I also like to point, and I also have some samples that I'm going to show you. So this first slide is really an overview of our project, and the title is really descriptive of the objectives, threefold. We were trying to develop resins and sizings that were designed for vinyl ester carbon fiber composites. We were trying to develop technology for prepregging. Obviously, there are many composite fabrication methods. We were really focused on prepregging because we wanted to develop technology for the high-speed production of automotive parts like this hood inner on the right-hand side of the slide that's actually been cost modeled by IACMI. And third, we wanted to demonstrate advantages relative to epoxy carbon systems, which are really the incumbent when it comes to many prepregging applications, both automotive and non-automotive. Really, our motivation going into the project, we felt that vinyl ester resins could offer some significant processing and cost advantages relative to epoxies and other prepreg systems in terms of processing and molding times. And also just looking at previous work, we felt that there was room for significant improvement in the resin fiber interface, which in turn influences the mechanical properties of the composite. So we assembled this project team consisting of 3 industrial partners and 2 IACMI centers. The industrial partners were Ashland, our resin supplier. We were also responsible for mechanical and thermal analysis. Michelman was the sizing supplier, and Zoltek was the carbon fiber supplier. So we really had brought together the 3 elements that you needed for an optimized system. The 2 IACMI centers were Michigan State, which was responsible for characterization of the resin fiber interface, and UDRI, which was responsible for fabrication and molding of Prepreg Surrogates. And I'll tell you what that means in just a second. I'm going to do a couple of acknowledgments, and I'm going to do the first ones here. In the right-hand column here, I've actually listed all the members of the project team from the various partners. And if your name is on the right-hand side of the slide, would you please stand up for a minute? Doing this for 3 reasons. First of all, these are the people that did all the work. I get to tell the story, but they did all the work. Secondly, if I get asked a question that I can't answer, I now know where they are in the audience. And then thirdly, I'll be up here and for the rest of the meeting able to answer questions, but I wanted to let you know that there are other people in the audience that you can talk to about this project. So Jared, you sat down, but I want you to stand up again for just a second. This is Jared Stonecash, and he didn't know I was going to do this. But you can see that one of the responsibilities for UDRI was project management. I was in effect the project sponsor. Jared was really the project manager, and there was a lot to manage. During the course of our project team met 25 times by either WebEx or in person, and Jared coordinated all those meetings. He kept samples moving between all the different partners, kept us all rowing in the same direction. In short, he did an excellent job as a product manager, and I want to thank you for a job well done. So, I have about 25 minutes left. I'm going to cut to the chase here and tell you what our team demonstrated. We demonstrated a prepreggable vinyl ester carbon fiber system that contains no styrene, that has a long shelf life at room temperature, no need for refrigeration, fast cure and compression molding, an improved resin fiber interface and mechanical properties, a reduction in the amount of processed scrap that needs to go to a landfill, a reduction in embodied energy, and you all add all that up and you end up with a cost-effective system. I'm going to tell you about each of these sub-bullets in the next 15 minutes or so. So a little bit about the materials we used. The resins were 2 vinyl ester resins from Ashland. They are both monomer-free, styrene-free vinyl ester resins that were designed for prepreg fabrication by the hot melt method. Aerotran 901 is based on bisphenol A. Aerotran 902 also contains BPA, also has more Novolac character, so it has a high glass transition temperature. Before I leave the resins, I just want to highlight the styrene-free character of these resins because that's becoming more and more important all the time. Many resins, vinyl ester resins, unsaturated polyester resins that you will find in widespread use in industry contain significant amounts of styrene. These resins don't. The sizings came primarily from Michelman, the sizing supplier, and also from Zoltech, who has an internal sizing development group. They can be described as aqueous resin dispersions, and we investigated multiple chemistries trying to enhance that interaction between the resin and the fiber. The fibers came from Zoltech. They were Panex or PX35 fibers. They were industrial grade fibers that came to us in a 50K tow with the mechanical properties you see here. And we also investigated two different winding configurations, T grade and W grade, and I'll say a little bit more about that later. This process flow diagram shows how the project flowed. As I said, most of the sizing development work was done at Michelman's laboratories in Cincinnati. They would send experimental sizings to St. Peters, Missouri, where they would be applied to the PX35 fibers on Zoltech's pilot sizing line. Those size fibers and the matrix resins from Ashland would then be sent to Michigan State, where they prepared short beam shear specimens. And that was really the first screening test for any resin sizing fiber combination. We would then down select systems based on the results from Michigan State. They would go to UDRI for prepreg surrogate fabrication and molding, again using fibers that had been sized by Zoltech and the matrix resins from Ashland. And after molding, samples would be sent to Ashland's labs in Dublin, Ohio for thermomechanical testing. So now you get a feel for what Jared was managing. Just a little bit about the short beam shear testing at Michigan State. They prepared these specimens using a wet winding process and the equipment here. They would take these samples, laminate at them, and mold them to produce short beam shear samples where they measured the interlaminar shear strength. That's a good indicator of the resin fiber interface, and it was used to down select systems for further testing at UDRI. In addition to the vinyl ester systems, MSU also tested an epoxy system as a benchmark. And here are the ILSS results from Michigan State. They tested a total of 26 different combinations with 2 different matrix resins and 13 different sizings. The y-axis here is interlaminar shear strength, and you can see that many of the systems had ILSS values approaching 100 megapascals, which is a good indicator that we were developing a strong resin fiber interface. We use this data to down select systems for further testing. Those are the ones shown with the asterisks. Naturally, we were picking systems with high values of ILSS, but we actually also picked some other systems with lower values because we wanted to see how well the results at Michigan State correlated with the results at UDRI, and they correlated quite well. We also did some comparisons to other values, and one of the things that Michigan State did was to run an epoxy control with an amine cured epoxy system that they had some familiarity with. They used the same PX35 fibers. That's the purple bar here. We also looked into the literature for other values for ILSS, for vinyl ester resins, and the highest value we could find was about 84 megapascals. And again, many of the down selected systems had values higher than either the purple bar or the red bar. And again, we took this as evidence that we were forming a good resin fiber interface. So just to summarize the down selection process, MSU tested 26 different combinations. We down selected it for 7 for testing at UDRI, and then we picked the best performing system. So now we're going to move from Michigan to Ohio and talk about the preparation, molding, and characterization of prepreg surrogates. So I've used this term several times, prepreg surrogates. None of the partners actually had a full-scale prepreg machine. Also, many of the spools of experimental sizing, we were working with just one spool. So we couldn't make prepregs, we made prepreg surrogates, and this is how we did it. We would take the sized fibers from Zoltech and spread them and dry wind them on a mandrel, and then actually cut pieces of the dry wound fabric. And at the same time, we would be taking the resin films and using this hot melt coulter to produce those films at 170 degrees Fahrenheit. UDRI would then take and produce this alternating stack, which we referred to as a surrogate. And you can see that there are alternating layers of carbon, fiber, and resin. And so we had all the ingredients of a prepreg, but they were in different layers. And in an actual prepreg, the resin and the fiber would actually be in the same layer. So to get from here to here, UDRI would do a debulking step in a heated vacuum oven. Then they would get something closer to this cartoon, which they would then compression mold, typically at 325 to 350 F, and they would produce 12-inch square plaques for thermomechanical testing that would be shipped off to Dublin. Just want to talk a little bit about stability before I leave this slide, because we found that these resin films and these prepreg surrogates were extremely stable at room temperature. And that is not typically the case for epoxy systems, which have a limited room temperature stability and often need to be stored in a freezer prior to use. And when I talk about stability, this is what I mean. Here are some DSC results from Ashland's lab in Dublin. What the y-axis here is the percent uncured material. And you can see for Aerotran 901 and 902 over a course of 9 months. And there is basically no change in the stability of these films at room temperature over 9 months. The same is true for the prepreg surrogates. Again, 901 and 902, the surrogates were actually made after the resin film, so this is a 7-month test, but you can see that there is virtually no change in the stability of these prepreg surrogates over 7 months at room temperature. And it gets even better than that. I mentioned that we didn't have an actual prepregger, but outside the scope of the IACMI project, Ashland actually contracted a company called Renegade Materials in Miamisburg, Ohio. They took our Aerotran resin and tried to make prepregs using their hot melt equipment. Now in these experiments, there was no attempt to optimize the sizing. All we wanted to see was, were our resins processable? And Renegade was able to show that they definitely were, with both carbon fibers, and with glass fibers. Acceptable processability, acceptable handling, acceptable tack. And I just want to hold up some samples here. I show pictures there of a carbon fiber prepreg and a glass fiber prepreg that were prepared at Renegade. Okay? This was done in February of 2016, not February of 2017. So next month, these prepregs will be 2 years old. Okay? And they're still very, very flexible. You can come up and touch them after the meeting. And you could take them down to Corktown tomorrow or out to Michigan State this afternoon and mold them. Okay? That is very different from epoxies, which typically have to be stored in a freezer. And so they aspire to get long shelf life stability at room temperature, long out time. These vinyl ester resins already get you there. Just a couple of other processing considerations. These are a little bit more subjective, but they did factor into our decisions. I mentioned the 2 different configurations, W grade and T grade. What the researchers at MSU and UDRI found were that the W grade fibers were much easier to work with than the T grade. What we were trying to do was spread the fibers and get the resin to infiltrate into the fibers. Okay? And it was much easier to do that with ribbons than with ropes. They also found that the sizings affected the processability and handling of the fibers. Things like spreadability, things like stiffness, we use the term boardiness, or the ease of alignment of the fibers. And although these things are somewhat subjective, we did take them into consideration when we were down selecting systems and picking the best performing system. So a little bit about compression molding at UDRI. As I said, they produced 12-inch square plaques, typical molding conditions, 325 to 350, pressure of 100 PSI. I guess I'll move over here for a while. And a typical molding time of 3 minutes. At Ashland, we've demonstrated molding times as short as 90 seconds, but UDRI typically use 3 minutes. And for some of the tests, they use longer curing times for some of the mechanical tests. We looked at 2 different architectures, biaxial and unidirectional. And before UDRI would ship any samples off to Dublin, they would do some QC. And They would do photomicrographs. You can see the laminated structure of some of the molded samples here. They would also measure the void content, which typically was less than 2%. They would then carve up the samples and ship them off to Ashland for thermomechanical testing, and typically we were doing 5 replicates of each of the mechanical tests. This chart here really summarizes the whole scope of the mechanical testing that we did at Michigan State, UDRI, and at Ashland. You can see the ASTM method and the architecture that we used. In the interest of time, I can't go through all the mechanical property results, but they will be included in the final report. So here is a summary of the mechanical properties of the best performing system, which we labeled 901K. You can see that we measured both resin-dominated properties like in-plane shear strength and fiber-dominated properties like flex strength and modulus, tensile strength and modulus. And overall, the group was pleased with the mechanical properties that we were seeing. We were also pleased to see the microstructure that we were getting, because here are the fracture surfaces of 2 of the in-plane shear specimens. You see good contact between the resin and the fiber. Again, further evidence that we were getting a strong resin-fiber interface bond. So again, in addition to internal comparisons, we tried to do external comparisons and look at epoxy values that were in the literature. When we did this, we tried to do what we called apples versus apples comparisons. We tried to make sure that we were comparing the systems that used the same Zoltec fibers, that were using the same architecture, either biaxial or unidirectional. And when we found those systems, we would normalize the fiber-dominated properties to 60 volume% fiber. And this spider diagram here compares the vinyl ester results for the best system versus the epoxy benchmarks, where the red pentagon is the epoxy benchmark and the green pentagon is the vinyl ester results. And in the worst case, the lowest case, the vinyl ester resins gave about 85% of the values of epoxy, and in the best case, the highest values were about 50% higher. So overall, the mechanical properties are good. And it's important to point out that the team is very confident that the properties would improve even more when we replace prepreg surrogates by actual prepregs, and we're going to talk about that in a few minutes. So now I want to switch gears and talk a little bit about recycling and embodied energy considerations, because there were some pretty significant findings here. Start off by reminding you that 2 of IACMI's major objectives are related to recycling and embodied energy. First of all, they want to increase the recyclability of composites into useful products by 80% by 2020. And they also want to reduce the embodied energy by 50% versus current technology. Both very ambitious goals. But what we have found in our project is that the use of vinyl ester prepregs can help in a big way to achieve those goals. And the reason really comes down to differences in chemistry between epoxies and vinyl esters. Because unlike epoxies, which are cured with either an amine or an anhydride co-reactant, these vinyl ester resins do not undergo cross-linking during the production and storage of a prepreg. I've told you that they are produced at a temperature of about 170 F, and then they are cured during that compression molding step at between 300 and 350 F. That means you have a big temperature gap between where they are produced and where they are molded, and an even bigger temperature gap between where they are molded and room temperature. And that's what leads to the extreme room temperature stability. And this is really a differentiator from epoxies, because again, they have to be stored in a freezer to prevent this cross-linking from occurring. And it's this absence of cross-linking that leads to advantages. I've already told you about the shelf life stability, but it also leads to advantages with respect to recycling and reuse. And here's some work on recycling that we've done in conjunction with Vartega, and I think Andrew Maxey's in the audience there. Vartega's focus is really on recovery and recycling of carbon fibers from prepreg scrap. and their technology involves a multi-step extraction process. What we did was to send some of the Renegade Prepreg to Vartega to run in their process. And they found that they could easily remove the resin. They took this Prepreg from about 35% resin down to 1 to 2% resin without any optimization, showing that the vinyl ester resin is readily removed from the Prepreg scrap, much easier than it can be done with epoxies. And that's not unexpected based on the fact that you don't have cross-linking. You can do this with just extraction. And although Vartega was focused on recovering the fibers, it should also be possible to recover the resin in a usable form. And that's going to be the scope of some future work. So that was recycling. Now let's talk about reuse, because we've also demonstrated that you can reuse the vinyl ester prepreg scrap. Okay? What we've demonstrated is that it's possible to compression mold this scrap, and here you see a cartoon where the gray part would be the scrap. What you've done here, what we've done is actually chop this up into small pieces and then actually compression mold it. So I've taken 2 of those prepregs and I've got samples here that have been compression molded 23 months after the prepregs were prepared. We've also demonstrated that co-molding with SMC or sheet molding compound is also possible. And this can be done with either virgin prepreg or with prepreg scrap. So what I'm showing here is a sample that is vinyl ester prepreg on this side and Class A SMC on this side. They have been co-molded together, and I'm showing both sides of the sample here, okay? And it's also possible to take, again, pieces of scrap. In this case, is I've taken strips here and actually selectively reinforce SMC and co-mold the SMC and the vinyl ester prepreg. So why is this possible? It's possible because the chemistries are very similar and the molding conditions are very similar. The time, the temperature, the pressure, the catalysts. So it becomes possible to co-mold material even when it's in scrap form. And just to summarize how vinyl esters can reduce processed scrap, I've made a distinction here between expired prepreg and cutting scrap. Okay? Because with epoxies, what you'll see is that they will expire as a function of time, or they can make out of spec material, and all that needs to go to a landfill. But with vinyl esters, they won't expire the way that epoxies do. And even if they do, or you produce out of spec material, you can enable facile recovery by an extraction process. With respect to cutting scrap or offal, which is the gray material in this cartoon, the piece is not used to make a part, again, that usually goes to a landfill. But with vinyl esters, I've shown you that you should be able to mold or co-mold that scrap, or again, if you want to, you can try and recover the carbon fibers and also get the resin in a usable form. So this is really a big differentiator between vinyl esters and epoxies, and it really can translate into cost advantages, because now you're getting some value out of your scrap, and you're not spending money sending your scrap to a landfill. This has embodied energy implications. And what we've done here is to actually use the FRPC tool that has been developed by Sujit Das and Christina Armstrong at ORNL as part of the IACMI program. And Komal Kudavali at the University of Tennessee and I have used that program to compare the embodied energy of compression molded prepregs made with styrene-free vinyl esters and epoxies. And this table here really summarizes the results of some of the calculations I've done. I've done calculations at 30% processed scrap, which is the value you most commonly hear for prepreg scrap, and also at 40% scrap, which is actually the default value in the FRPC calculator for manual prepregs. In these 2 columns, I've compared the percent of the vinyl ester that's reclaimed and the percent of the epoxy scrap that's reclaimed. And I've assumed that these numbers are bigger than these numbers because of what I've just told you about reuse and recycling. And if you go through and do the calculations, you see that some very significant reductions in embodied energy should be possible with vinyl esters. The values range from 6 to 33%. Okay? Now remember, IACMI's goal is 50%, so we don't get you all the way there, but vinyl esters can take a big chunk of that 50%. So just in summary, we have shown that vinyl ester carbon fiber prepregs have an attractive value proposition from a processing standpoint, from a molding standpoint, from a recycling and reuse perspective. And all that adds up to what we believe is a cost-effective alternative to epoxies. So, what's next? Well, we've done a stage 1 project. We're interested in doing a stage 2 project. Why? Because we have an attractive value proposition. The stage 1 work has been done with surrogates, not actual prepregs. We actually want to demonstrate utility in an actual part, not plaques. We want to do more work on the recycling and reuse front. We've done proof of principle. We feel there's a lot of work to be done with optimization, and I'll talk about this later, but everyone on an IACMI team is leveraging everyone else's resources and funding. So, we have 3 different options for a stage 2 project. One is a comprehensive project where we will be looking at forming prepregs and molding prepregs with that optimized system and also looking at recycling. We also have a version where all we're doing is looking at molding of the prepregs, and we also have a standalone project focused just on recycling. And all 3 of those are summarized in this complicated diagram here, which I don't have time to go through. But suffice it to say that there's a potential role for all the stage 1 partners, and we would be looking for new additional partners to put in those red boxes. We would be looking for a prepregging partner. We would be looking for an automotive or a tier 1 OEM with a specific part in mind, and we'd also be looking for recycling partners. So if you're interested in being in any of those red boxes, please see me before we leave Detroit. What else is next? Well, we want to complete the final report. Our project actually ends on January 31st. So final report is due within 90 days. I've talked about defining a stage 2 project. We also plan to participate in the ACMA's conference on recycling in April. I'll have more of an opportunity to talk about the recycling and reuse than I did today. And we also want to pursue non-automotive opportunities for this technology. I mentioned that it was focused on the automotive market. We believe that some of the benefits that we've demonstrated could make this an enabling technology in other areas, like infrastructure repair, where you could take patches out into the field and not have to worry about shelf life. Also, an alternative to filament winding for the production of tanks or rollers. In aerospace, we are not going to replace epoxies in the fuselage or the wings of Dreamliner 787s. Okay? But Brian Rice at UDRI has made us aware of some less demanding unmanned applications where this technology could represent a low-cost alternative. And if any of you have any other ideas based on what you've heard, I'd love to talk to you. Just want to finish up. I'm kind of preaching to the choir here, but this is for the people who haven't engaged in an IACMI project yet, or maybe there are some potential members who are considering joining. In addition to the technology that we've gotten out of this project, there have been other benefits. And I listed them here as connections, opportunities, and leverage. Okay? IACMI has done a great job of connecting us to partners. Okay? They were the ones that connected us to Michelman and Zoltech. We knew about Michelman and Zoltech, but IACMI connected us to the right people to talk to about this project. Further into the project, they've connected us to the recycling companies. And outside the scope of this project, Byron Pipes has connected us to modeling companies that we should be talking to. Also, in terms of new opportunities, we're involved in this project. We've also been pulled as a resin supplier into 3 other IACMI projects. In fact, Henrik Meinke from Volkswagen is going to be talking about the SMC liftgate project next, and we're the resin supplier for that. There are also 2 other projects that are close to being approved. So being involved in IACMI has opened up new opportunities for our resins for applications and processes. And then lastly, leverage. We've had access to existing equipment at places like Michigan State and Zoltec and UDRI. We didn't have to buy it ourselves. We didn't have to move up the learning curve ourselves. It already existed. And then we were leveraging money from the DOE, from the state of Ohio, and the other industrial partners. And those leverage factors are pretty attractive. I just want to finish up with some acknowledgments. Again, I want to thank all the people in the right-hand side here. They're the ones that did all the work. I also want to thank Renegade Materials and Vartega for their help with prepregging and recycling. In terms of funding, I would like to acknowledge Kelly Visconti and her staff at DOE, and also Glenn Richardson from Jobs Ohio for their funding support. I should point out that the funding from the state of Ohio actually was very important because it helped us expand the scope of the project during the formative stages. And then I want to acknowledge a host of people from IACMI. I'm not going to read you all of their names, but I especially want to thank Cliff Eberly and Dale Brocious for many helpful conversations and for general guidance. And thanks to everyone for all the support you've provided on this project. That really concludes my presentation. I'll be happy to answer any questions. I'd like to thank you.
If there are any questions, we have microphones roaming around. Please make sure you raise your hand.
I have a host of samples here if anybody wants to come up and talk to me at the break. Yes?
Try to speak loud. You didn't mention anything about the cost for the epoxy versus the vinyl ester. Do you have any estimation where you end up there?
So it's really not appropriate to talk about cost in a forum like this, especially when there are competitors present, okay? But I will happy to have that conversation with you afterwards.
I appreciate that. Thank you.
It's cost effective. Any other questions? That's the standard Ashland line. Yes, I think I saw one over there.
So I saw your flexural properties less than tensile. That didn't look consistent. Was that a 3-point flexure test you did? Or?
So I think what you're referring to is the best system. The tensile properties were done with unidirectional samples, and the flexural properties were done with the biaxial samples. And the reason I showed those was so I could compare them to epoxy systems with that apples versus apples comparison.
Just a comment on interlaminar shear. Do you think that's reasonable for interface characterization?
Is Larry Drizel or Mike Rich here? Because they're really the experts in that method. Larry?
Yeah, for a project like this where you want to be able to make these distinctions between these very large combinations of systems, surface treatments and so forth, it's an excellent screening tool. One can go deeper and get individual single fibers if the resin systems will cooperate with you as well. But we're pretty convinced that these are sensitive enough to the interfacial conditions.
All right. Thank you very much.